Welcome to Thermo. Energy and motion. In this talk, we'll follow how energy moves, how heat is transferred, and how mechanical systems convert energy under physical laws. Think of this as a guided tour through heat transfer, energy conversion, and the rules that constrain engineering choices, with illustrations to make each concept intuitive and connected. To speak thermodynamics, we need a simple vocabulary, a system, its surroundings, and the boundary that separates them. State variables like pressure, temperature, volume, and mass describe the system at a moment in time, while process paths show how the system moves between states. The slide's diagram ties these ideas together and frames equilibrium as the reference point for changes. Thermal equilibrium gives temperature its meaning because it's a transitive property. If system A equals B and B equals C, then A equals C, so a universal thermometer scale can be defined. That shared baseline becomes the anchor for energy accounting, letting us compare and quantify heat and work across different systems consistently. The first law is simply bookkeeping for energy. The change in internal energy equals heat added minus work done, written as delta U equals Q minus W. Energy can move or change form, but the total always balances, like entries in a ledger. This principle lets engineers track where energy goes and ensures no mysterious gains or losses. Entropy introduces direction into physical processes. Heat flows spontaneously from hot to cold, which limits the maximum efficiency of engines and guarantees waste heat. That irreversibility is what gives us an arrow of time, making past and future distinct and setting practical limits on how well real systems can convert heat into useful work. Absolute zero is an asymptotic ideal. Entropy differences shrink as temperature drops, but perfect order and 0 Kelvin cannot be reached in a finite number of steps. The thermometer and staircase illustration remind us that cooling progresses in finite moves toward an unattainable limit, so absolute zero remains a useful theoretical benchmark rather than a practical destination. Thermodynamic cycles show how engines and refrigerators operate. Heat engines take heat from a hot reservoir and produce network, while refrigerators move heat uphill using work input. The Carnot expression, eta equals 1 minus T cold over T hot, defines the ultimate performance ceiling, showing that efficiency depends only on the temperatures of the reservoirs. Real processes fall short of ideal cycles because of irreversibilities like friction, finite rate heat transfer, and turbulence. These effects generate entropy and increase disorder, producing efficiency losses below the Carnot limit. Recognizing where entropy is produced guides engineering redesigned to reduce losses and improve the practical performance of machines and systems. Every kilowatt has a pedigree and a price. Sources, conversions, and losses all matter when we innovate. Nature's thermodynamic budget is non-negotiable. So, successful innovation works within those constraints, optimizing where possible while acknowledging unavoidable limits. This perspective helps prioritize designs that deliver real gains without violating fundamental energy accounting.